Hello, and welcome back to my 486 project. Before we get started, I just want to say that it's been a kind of an exciting few days over here. I never expected the channel to get noticed, to be honest. The fact that it's been posted about in a few tech blogs and people are actually watching this and making some very nice comments and very helpful comments is amazing. It's more than I ever had expected, so thank you. Thank you for watching, thank you for enjoying it, and thank you for leaving the kind words. And there's been some great suggestions, and some of them, well, I say suggestions, some have been suggestions, some have been pointing out where mistakes I've made or areas that could have potential long-term problems. And so those will be addressed slowly going forward as I integrate certain things as well as redesign certain things. But needless to say, I am listening to everything you're telling me, and I appreciate it so much. I really barely know what I'm doing with this, so I just appreciate it. So thank you for being here, thank you for watching, thank you for enjoying. Alright, so moving on. Recap of last time. Last time we made this. This is the data bus controller. This takes in the data bus, or the data on the lower 8 bits of the data bus, and shifts it to the other bytes of the data bus, depending on what the CPU asks for. This is a fairly straightforward one. It doesn't need, in theory, I want to be clear on this. In theory, it should not need 4 buffers. This one should be clear to write back and forth, because when the CPU writes to something that's not the low byte of the address bus, this should never be enabled. So we shouldn't have shouldn't have different data driving the lines. I don't know if that's correct or not. I believe it's correct, but if you notice, I made sure there's more than enough room to put another buffer in just in case. So if a fourth one pops up, you know that's why. So this works. It routes the data very nicely. So the next step then is going to be getting the ROM integrated. And the ROM has a couple of control systems attached to it as well. And it's not so much, well, they're necessary part of the overall bus control, but the ROM is the first place it makes logical sense to implement them. Now the first one here is going to be our 74138. This is a 3 to 8 decoder. Now we're feeding into this the write read, that always comes off backwards in my mind, line, the data control line, and the memory I/O line. And it's controlled by the address data strobe line. Now these generate the 7 control signals that we need for controlling the data bus. The int acknowledgement line, which we'll get into interrupts a bit in later. It's simple and complicated at the same time, and we'll talk about it as I get to it. The halt, which is a little bit more than the halt. It actually is more of a special bus cycle, but halt's the one that gets used 99% of the time. So I/O read, I/O write, which is reading and writing to the I/O side of the bus. The code read, data read, and memory write. And this is just reserved. It doesn't do anything. Now, as I said before, the code read and data read differentiate reading the actual opcode data. So when it's actually, reading the opcode to execute is under code read, and reading any other data is under data read. Now, some experimentation seems to indicate that the code read is only used for reading opcode data. So if you're reading from the code segment, which if you don't know what that is, I will be going into more in-depth on the memory structure of the 486 later on. But it means is that it's only used for reading opcode data, not for any kind of memory reads, even memory reads of code. Which is fine, you can still use it to separate out the code and the data spaces, but it doesn't mean that there's no way to read data from the code space as data. Now, we don't care about that. We're not using that, just like most uses of a x86 don't use it. So we take those 2 read lines and put it into an AND gate, which then generates our memory line. Now since the output of this is always going to be high if not used, and active low, it means that if either one of these are used, it's going to be low. If neither of them are used, they're both going to be high. So the AND gate works perfectly. So both high, memory's high. If either one's low, memory is low. So, one interesting caveat here is the address data strobe. Now this line goes active, which is to say low, when the data for the address bus is asserted onto the bus. That's going to be the address lines, these three control lines, and the byte enable lines. Now, it goes high on every other bus cycle, which includes the read and write cycle, so anything involving data. This is important because we have this set up so that we're using the high state of this line to activate the output of this, because that's when data is valid. That's when the data bus is valid. So we don't want to, if we left this always active or active when it was low, we would be pushing data on the data bus when data is not valid, or reading data from the data bus when data is not valid. So you can see where that could have some long-term problems. So that is the basics of this simple controller. This is just 2 chips. For the ROM itself, we just have 1 chip, and an inverter. We take the A31 line and invert that to generate the output enable signal, which basically means that if the high bit of the address space, which is the top 2 gigabytes of the address space, will be mapped to ROM. And there's only 32K of ROM, so it's going to be repeated a lot. Now, when I get to like a breadboard, I would want to be a little more limited. When I get to a PCB, I would want this to be a little more limited. I don't want to have the entire space taken up by the ROM, but for now, this should be fine. The memory line goes into the output enable line, and then it's just address line 14 through address line 0 is the address line, D0 through D7 is the data line, and the write enable line, which this is an EEPROM, so this is, you can use write enable to write very slowly to it, is just pulled high because we're not going to use it. Now, there is one interesting caveat here, in that we have these 2 chips here. We have an inverter and an AND gate. And this is basically 2 chips where we're using 1 out of 4 gates and 1 out of 6 gates. And to be perfectly honest, I also currently don't have any AND gates. So instead, I'm going to be using NAND gates, which are great because an AND gate also works as an inverter. So we will be using 1 NAND gate to make the inverter, and then 2 NAND gates on this one to make the output and 1 to invert the output to be correct. So that is the plan. So let's start by popping on the new breadboard here. All right, and connecting the power lines. And yes, I know they're the wrong color. I do need to get new. I'm out of red cable, I'm sorry to say, so I need to get some new red cable, and I can cut some appropriately colored power jumpers, as well as the ones for the ICs. At the moment, the color coding is for the size of the jumpers, so don't have everything I need there. So first and foremost, we're going to want the decoder. Let me make sure this is the right one. Yep, that's the 138. Put that right here. I'm going to leave 1 line free. We have our NAND gates, so put those here. And we have the actual ROM, which I will put here. Now, one thing I do want to do, due to how the output of the pins are of the ROM, I want to try to line things up for a little bit of a straight connection between the various points. There, that should do it. Okay, actually I'm going to move that just slightly because that's just a little too tight on one side and a little too loose on the other side. This is not the recommended tool for removing ICs, by the way. Okay, let's try that again. All right, there we are. That looks a bit better. Get that out of the way. So there's that. Next is I'm going to need some power jumpers. And as always, my data sheets, because I can never remember my pinouts. So now I should be able to use the orange ones for most of these due to these chips being oriented correctly this time. So that should work just fine. And luckily they all have the same power configurations here, which is always nice. So ground, ground, ground. Okay, let me just double check that. And yeah, and then power, power, power. Now, one interesting thing with the decoder is that the arrangement of pins, the output, actually makes it very easy to put an LED on it. I will demonstrate that in a moment. Oh, let me get the right sized one. Is that online? That's correct. There we are. And there. Okay, so yes. Due to the way the pin out on this is, which is on this sheet, where it's basically 7 pins here plus the 8th pin around here, we can easily drop, let's see, make sure it's an active high LED, there. And that will give us everything we need on that. That's nice. So, next we need to have, let's see, 1, 2, 3. Pull low, pull low. That will give us our enable lines. All right, and then what's the last one I need for this? I need to output right enable to high. We use a yellow one here just to make it easier to spot so I can use it for counting positions. Okay. So we're good here. Wow. Now we need to start getting some wiring going on. So I'll give you a brief overview of the wiring before I get into it, just because I'm probably going to once again fast forward it just because it's a lot to go over. It's a lot to do, not a lot to go over. So these are going to be dummies for the address pins. The address pins will connect to here. Now, we do need to run address line 1 and 2 up to over here, or 0 and 1, sorry, because otherwise the decoder won't work. This particular control line has to attach to the right read line, which goes to here. The output of these two, I say these two, I randomly point to the chip. Which of these two are these? Of the the 2 read lines need to go obviously through the NAND gates. And we also have to have the input for the address line go to the NAND gate. So let's get the NAND gate quickly wired up because that's worth explaining, and then the rest can kind of be done as I go. So we'll pull up the NAND gate pinout because, as always, I forget these things if I don't have them right in front of my face. So there's that one. Is that long enough, or do I need to go slightly longer? I need to go slightly longer. So that one goes. That's still not long enough? That is still not long enough. That is annoying. It was the right length when I tested this. You gotta love it when things don't quite work out the way you thought they would. I probably put it in a slightly different location. That's annoying. Well, I will make do. You know, live. Not even television, it's just live. I laugh because I am frustrated. Okay. You know what? I am just going to jump into my backup emergency set of cables, because of course I have a backup emergency set of cables. Okay, this should be more than enough. Now these are not as high quality as my other current lines of current cables, so that's generally why I haven't been using them. Okay, that is one, and the next one is that one. Okay, so all right, that is 6 and 4. 6. Yeah, 6 and 4. That matches what? That matches that. So 6 and 4. Now we need to take the output of that and jimmy it into the next inverter. So that is there. Come on, I know you're right length this time. I can see it. All right, that is correct. And now I need a small one to jumper the extra 2. Come on, get in there. All right. Goodness, I am fumbling everything at the moment. All right, there we are. And so that gives us our control line, which then feeds into here. Might as well get that taken care of at the moment. So here we are. Let's see, this is our output enable. That's pin 22. So 13, 8, 9, 11, output enable. All right, that one goes to there. Is that the best choice I have? Is this shorter? This is shorter. Let's just go with the shorter one. Okay, so 13, 8, 9, 11, output enable. All right, and there we go. That gives us that, and then this one will connect. So we'll put the address line coming into this one. Didn't need to do that. That is going to be these first two together. And we'll output, that output line goes to the chip enable, which is that one. Okay, so that gives us our control lines. And the last control line we're going to need is this one, which will go down to here, which will connect to the output. Which I should probably just be able to stick it there. It seems like a little bit better. Okay, so that takes care of that. Now we just need to wire up all the address lines and all the data lines. So now that I've demonstrated my inability to properly wire things, I'll go into a time lapse for the rest. So I will be tending to that right now. Okay, that does look like it should be correct. So to give you a quick overview of what I have here, because I think I had the data sheet pretty much off camera the entire time, so oops, I will obviously have to include it in the camera view. So, you know, the data lines just go straight across because they are 0, 1, 2, 3, 4, 5, 6, 7. Actually, you know what? There you can see that now. Can you? Is it in focus? It's good. Okay. So I have 0, 1, 2, 3, 4, 5, 6, 7. Then we have the address lines of 0 through 7 here. Then it kind of starts jumping around. Now, in theory, I could have plugged the low 8 bits of the address line directly into this side of the bus, but this arrangement is different from what I have for the RAM chips I'm using. Why am I getting those backwards half the time? Whatever. As such, it's easier to do it this way because then I can feed the appropriate lines down into the RAM boards when the time comes. So, now comes the fun part, seeing if I did it right. And let's be honest, we're all hoping I didn't do it right. I'm half hoping I didn't do it right. Making mistakes sometimes is more interesting than doing it right the first try. So, first and foremost, let's get the power in. Make sure I don't put it on backwards. Now, I am going to try to improve the overall arrangement of wiring here to try to make it a little easier to see what I'm doing, but there's only so much I can do just because, well, I don't have a lot of room for it. You know, sometimes I'm not fantastic at things. Oh, and lastly, I'm going to need the address lines. If I forget that, things will work weirdly. Okay, next. Address lines. Now I'm going to try, actually let's pop this off for a second here. I'm going to try something slightly different, and I'm going to run the address lines underneath everything because they're fairly long and flexible. Now I don't know if I can do this in the long term, but for the short term this should be okay. And lastly, I'm going to need the address line 31, which will tuck there. So pull this off, drop that there, pull that off, drop that there. Okay, that's grounded, put that there. Okay, so that looks good. I don't think I've disconnected anything. Double check. All right, good. And this goes here. All right. So, control lines. That's these three here. Tuck them back under here, and they go that way. And then there's the address data strobe. That goes there. Okay, so next is going to be the data. And this is what's going to cause most of the obscuring of things. I do need to get slightly shorter connectors. I do have the appropriate tool to make connectors now. It's just that, you know, these are not the worst choice in the world, and you know they're all connected like this, so it works out nicely. Okay, there. So that looks right. So that's there. Address lines. Now there's a 50-50 chance I got these two lines backwards. I do it way too often. So now one last bonus thing. We need to see if this is doing anything at all. So I'm going to add one extra connector here. So I'm going to take the data lines here, and I'm going to hook them up here. And I'm going to do a connection to the IO write pin, which I believe, let's see, int read write. All right, IO write. So the code I have in the ROM right now just writes out to the control port, an IO port. It doesn't do anything there. It just increments a register and outputs it. But the idea is that it should demonstrate that it's doing something. Come on. I got new breadboards, and some of them are still fairly stiff in places. Okay. All right. Verify that's all wired in. See how it looks on camera. Okay. All the LEDs should be visible. Okay. Deep breath. Let's power it on. Well, first and foremost, that is the wrong line. Reset it. Well, disappointed. So, after coming back and checking all my connections, I think the thing I did was the thing I said I might do, which is I got these two lines backwards. That the address line 1 and address line 0. I do this all the time. It's kind of weird because that one is address line 0, address line 1. You would think they're in order. You would think that it'd be easy enough to work with it. So let's turn it on again and cross fingers. All right, it's resetting. It's running. 1, 2. It's working great. Fantastic. Let's dial the speed down so we can actually get to watch that. Okay, fantastic. Now the code that's on the ROM here, which it's fairly small, so I'll just put it right here. It just jumps back a bit and just updates, increments the register and outputs it to the I/O port. It's just a great way of showing it that's doing something. But there is one interesting catch. Due to the overall structure of the memory space, x86 starts booting up at the high 16 bytes of memory. Now, when the original x86, this is the this is the first 16 bytes below 1 meg. On a 486, it's the first 16 bytes below 4 gig. This creates a problem, though, in that it boots into a compatibility mode, which is real mode, where it can only access the first 1 megabyte of memory. So when it starts up, it puts it into a special mode that even though it's running in 16-bit mode, in compatibility mode, and it thinks it's accessing the bottom of 1 megabyte of memory, it's actually accessing the bottom of the 4 gig RAM area. And it does that up until you do a long jump. A long jump being a call, a far return, or an interrupt, or a couple other things, which resets the memory space. So part of what this does, the jump backwards, is to ensure that it works the way documentation says it does, in that we can do a short jump without screwing up the memory mapping and continue to access ROM, which means that we should be able to keep the ROM entirely in high memory and not have tried to have it mapped into multiple places, which can be something you have to do here. the easiest way to do it is shadow RAM, where it would just copy the ROM, some startup circuitry would copy the content of ROM into a very specific location in RAM, but I'd rather not implement that. But for now, though, this is working. It is actually running code. It is doing something, and it's doing the right something. So the next step is going to be to add RAM, which is just going to be 32K of RAM. Why do I keep inverting that? 32K of RAM, which goes at the bottom half in memory. And once we have that, in theory, we have a fully functional processor. I mean, it can't really do anything because there's no I/O, but we should be able to do more stuff. But that is for next time. And this time, though, I think we've made good progress. The ROM is working, and we can now start doing some more interesting things. And that includes the potential of going into protected mode. But I'm probably going to do a bonus episode sort of going over the rough memory architecture of the x86 for people who are unfamiliar with it. So I'll cover that more in depth there. But yeah, next two steps is RAM and protected mode. Until then, though, thank you for watching and have a good day.